With that, I'm going to kick it over to Stefan for his PHP hacking presentation.
Okay. It's okay. Can you hear me? Yes? Okay. So welcome to my talk about the state-of-the-art post-exploitation in hardened PHP environments. I first want to introduce myself. My name is Stefan Esser. I'm from Cologne in Germany, and I work in information security since 1998. And I'm actually a PHP core developer since 2001. You might know the month of PHP bugs that was organized by me 2 years ago, and in May. In May, I released, every day of May, I released at least one, sometimes two or more, vulnerabilities in PHP itself. So not in PHP application, but in PHP itself. I'm also the lead developer and maintainer of Suho, which is an extension to PHP. It's a patch and a PHP extension that makes PHP more secure against attacks. And I work at Sektion 1 GmbH in Germany, also in Cologne, which is a German web application security company. So first I want to give a little introduction about what this talk is about, because it's a little bit confusing to some people what I'm actually talking about. Let's start with the basics. The basic idea is that a lot of PHP applications that are installed on web servers, especially when you're a web hoster, you have no control about the applications your customer install. And a lot of these applications are very bad, and they often suffer of vulnerabilities that allow remote PHP code execution. This is usually due to a file or URL inclusion vulnerability. It's because people can upload files. For example, there's this framework called Hardened, which is used by a lot of people, and they will announce next week that there's a vulnerability in Hardened where every application that uses the form management of Hardened and uses image uploads, they have a problem in there, and you can upload files to anywhere on the web server with this bug. And so, of course, you can also upload PHP files, and if there's a writable directory in the document root, you can put PHP files in there and execute them. Another point is that a lot of PHP applications have injection vulnerabilities in eval, in create function, which is just an eval wrapper, and preg replace, which in combination with the e-modifier also allows PHP code execution. The last thing is sometimes there's an injection into call userfunc. One prominent example was a WordPress exploit for like 3 years ago, where it was possible to override the filters that were executed from the outside. So normally when an attacker is able to execute PHP code on a server and this server is not secured, then he basically can do everything PHP can, and PHP can do everything from reading, writing files, executing shell commands, loading libraries, so you basically can do whatever you want on the server. The moment the web server is hardened against attacks, this is not so easy anymore. And the thing is, more and more PHP environments today are hardened by default. So sometimes you have, like every new Linux distribution or OpenBSD, they all come with Suho patch by default. On some, like SUSE Linux, you maybe have an app aimer around the web server. And so many standard Unix distributions or Linux distributions usually come with more and more hardening in themselves. And when you are able to execute PHP code in this environment, then it's not so easy to take over the server anymore. It really becomes a challenge. And so now, what is this talk about? This talk will first introduce some of the common protections you will face on a modern web server. It will give an introduction to a special kind of PHP vulnerability, a local vulnerability in PHP itself, or let's say a class of local vulnerabilities in PHP itself. I will show how to exploit two, well, let's call it 0 days in PHP. They are not exactly 0 days because they are, I already talked about the same topic 3 weeks ago in Asia. And so these people already know the bugs. So now you learn the same bugs, and but I don't expect them to be fixed very soon because it's really hard or impossible to fix these bugs. I will show how to exploit them in a portable and stable way, and then I will show how you can use this vulnerabilities, which is actually an information leak vulnerability and a memory corruption vulnerability, and I will show you how you can combine them to disable or get around most of the common protections on web servers. Yeah, and when you want to get around kernel level protections, these techniques I will provide will enable you to launch kernel exploits if you have some. So the second part is, like I said before, it's an introduction to the common protections in hardened PHP environments. And so first, there are several kind of types of protections you will see on a web server. First of all, you of course will see protection against remote attacks, but because we assume that we already can execute PHP codes, these protections already failed. So we will not discuss them here. Then there are some protections that will limit the possibilities of PHP code, like the functions PHP can use. Then there will be limiting functions that limit the possibilities of the PHP interpreter, like AppAmmo, that limits the files PHP can open. There are a lot of hardening features in modern compilers and kernels against buffer overflows and memory corruption exploits. There are features in PHP that limit the possibility to load arbitrary libraries. And of course, you have some non-writable file systems that will also be a problem when you execute PHP code to access the server. So where do you find these protections? First of all, of course, you find them in PHP itself. You find them in the Suishin PHP security system. You will find them in the web server, maybe like mod security, in the C library, in the compiler and the linker, in the file system, like I said, non-writable file systems or non-executable file systems. And you can also find these protections in kernel or kernel extensions like GR security. I will go into these in a minute. So first we have the protections that are directly in PHP, and the most known feature or security feature of PHP is the safe mode. And the safe mode actually disables access to several sensitive configuration settings. It disables the possibility to execute shell commands. There's an exception. You can define a directory where it's allowed to execute shell commands, but normally it's disabled. Then you have a white and blacklist approach on the environment variables so that you can't just use an LD preload attack to get around the restrictions. It also limits the access to files and directories to the directories and files that have the same user ID as the script that is executed. Yeah, and some other things are done in safe mode. They are not so important. The thing is, because safe mode is poorly implemented in PHP, it's not backed by any kernel implementation, and so the problem here is that when the protection is directly in PHP, first of all the file access functions that PHP uses need to implement this feature, and in the past a lot of bypass vulnerabilities were disclosed where one of the functions forgot to do these checks. The other thing is that safe mode will be gone in PHP 6, so if you rely on safe mode with PHP 6, you have no safety net anymore. Yeah. And a very similar protection is the open base dir directive. Open base dir is similar in the way that it limits the files and directories the PHP script can access. You can define some base directory in which your PHP application is able to read and write. The next thing in PHP is that you can disable functions and classes, built-in functions and built-in classes. The thing about this protection is that it completely removes the function from the function table that is loaded at runtime, and it also removes the classes. So before this talk, no one ever managed to reactivate PHP functions from PHP itself. I will show how you can do this. The last feature in PHP itself, well, the last thing that is hardened is the DL function to load PHP extensions. And DL is just a wrapper around the DL C library function. And there are some limitations in PHP, in new PHP versions. You can disable this function. The other limitation is that you can only load extensions in the extension directory. And if you have a thread-safe environment, then this function is completely disabled because it only causes problems to load PHP extensions in a thread-safe environment. The last protection you see in PHP itself is a protection against buffer overflows or memory corruption. It's a hardening in the memory manager. And in old PHP versions, the memory manager of PHP is just a wrapper around malloc with an additional doubly linked list. And you could always exploit PHP applications even on hardened memory managers of the C library, because there was always the doubly linked list in PHP itself. And it has all the same unlinked problems that were fixed through hardening patches in the past. With PHP 5.2, the memory manager was completely changed. The people behind PHP, the Cent Corporation, they decided that they can do a better memory manager than the C library developers. So they created a really completely new memory manager that is thread safe. And yeah, of course, they put some modern security features in there, like a safe unlink, and they also have a canary protection, but it's normally deactivated. It's only activated in debug mode, but no one runs the production server in debug mode. So when you look outside of PHP, then you have Suoshin, and Suoshin also comes with a memory manager hardening. It's very similar to this thing in PHP. The difference is that it was there before, and it also works with the old PHP versions, and it always has canary protection. Additionally, there's also a protection on PHP hash tables. So in PHP hash tables, I will show this later, there's a field which is a destructor pointer, and many PHP exploits just overwrote the destructor pointer, and so arrived at code execution exploits. And actually in Suoshin there's a protection. It just, when a new hash table is created and the destructor is registered, it will record this, and later when a destructor is about to be called, it will look into its table and look up if this destructor is known, and if it's known it will allow the execution, and if it's not known it will not allow the execution. It will abort the script, abort the process, so that there can be any other problem. Another thing you have in Suoshin is the possibility to have something similar than disable function. It's similar only because it doesn't do it the same way. It doesn't remove the functions completely. It just checks on invocation of the function if it's allowed or not. And the reason for this is because virtual hosts often wanted to have one virtual host that is allowed to execute this function and one virtual host is not. The problem is with normal PHP that's not possible, because PHP removes this function completely for the whole process. The other difference is that in Suoshin you can have a separate black and white list to for evaluated code. So if you have eval statements or something similar in your PHP application, you can limit the functions these eval statements can use. Yeah, and the other solution features are really not important here because they only try to stop remote attacks against PHP applications. When we look at the C library or the compiler and linker protections, there are some things like stack variable reordering or canary protections of the stack. These protections are to stop buffer overflow exploits and memory corruption exploits. And there's a linker feature which is called rel-row. It will reallocate the segments in a executable, and the idea is that when you realign the segments, you can move some segments in the same place that can be switched to read only after they are used the first time. The problem is to do this realignment, there will be holes in the image of the executable, and so if you try old exploits that scan from the beginning of the memory to the end, from the code segment, try to get into the data segment by just going forward, they will crash because they will hit this non-aligned, non-allocated page. Of course, you have all these memory manager hardenings in C library. And normally in new C libraries, you also have obfuscation of pointers. So when you have this set jump and long jump functions, for example, then you can just change the structs on glibc because the pointers in there, some of the pointers in there are protected. The last protection that you will face as an attacker are the kernel level protections. Of course, there's the non-executable stack heap and data. You have address space layout randomization, which basically means that the mapped memory is not mapped at a predictable location, but at random locations. And you have a hardening of the mprotect function, so the idea is that once you have writable memory, you cannot make it executable anymore, which doesn't work on all platforms. You also have non-executable mounts. So if you have, for example, GR security, non-executable mounts are one of the ways to stop people from just dropping a binary on the web server and load this with executable writes into the memory. And then you have all these modules like AppAimer or the Apache module mod AppAimer. You have systrace, which tries to protect system calls. You have SE Linux and, of course, Jira Security. So before I will go into the actual PHP exploits, I will give you an introduction to the internals of some PHP structures. We will start with simple PHP variables. When you look at simple PHP variables, the first thing you will see is that there's a difference between PHP 5 and PHP 4. The actual difference, I hope you can at least try to read this. I think in the back you can't read this. The actual thing is there's only a little difference between PHP 4 variables and PHP 5 variables. The difference is that there's the order of the elements is a little bit different. The object handling is a little bit different, but we don't care about this because we don't use objects today. Then there's the reference counter, which is 16-bit in PHP 4 and 32-bit in PHP 5. But this is actually the real difference between these two structures. I forgot to mention, in PHP, these structures are called setWorld, CWIL. There's a flag or a type field in this structure that is telling PHP what kind of variable this is, and there are null values, there are long values, double values, Boolean values, arrays, objects, string, and resources. Resources in PHP are like file descriptors or network handles. There's one thing when you write exploits that you must keep a look at. Actually, between PHP 5.0 and 5.1, there was a little switch between the value for booleans and strings. They changed the place. The reason for this is because PHP 5.1 was supposed to be a lot faster than PHP 5.0, and they had a lot of micro-optimization put in. And one of this optimization was when you reorder these, like it's today, like boolean comes before string, then you can just check in the destructor if it's below or equal boolean. And if it's below or equal boolean, the destructor doesn't need to do anything because the whole variable is within the structure itself. All the types that come afterwards have external data, and so you need to take care of the external data. So one thing we will talk about today are PHP arrays. And PHP arrays are actually not really arrays internally, they are hash tables. And they are some kind of special hash tables because they also have two doubly linked lists attached. One doubly linked list is used for collisions in the hash buckets, and the other doubly linked list is to keep track of all the all the elements in the array. So otherwise, it wouldn't be possible to just go from one element to the next. The other thing is PHP arrays are auto-growing, so it will normally start with a size of 8 elements, and if it exceeds this amount of elements, it will auto-grow to the next power of 2. Yeah, no, like I said before, there's one interesting element in there which is called p-destructor. It's a destructor pointer, and like I said before, many old PHP exploits try to override this pointer to get just code execution. And normally when you have a PHP application, you have a lot of these PHP arrays in memory, and so it's very possible that you hit one of these pointers. Yeah, other thing is PHP arrays support, on the one hand, numerical index that are used directly as index in the buckets, and they have an handling of alphanumerical keys, which are translated into by the hash function, which is a DJEB hash function. It's a little difference between PHP 4 and PHP 5, but we don't need this difference for this exploit we talk about today. To confuse you a little bit more, here is an image, how this looks like in real life. You see you have the hash table, and the hash table is connected to an array of buckets, and each of these buckets, when it's empty, of course it's 0. When it's not empty, it contains the first element, and the first element contains a pointer to the next element, and the elements in an array are actually buckets, and the buckets point to the set values, to the PHP variables. And the dotted line, or the dashed line, the red dashed line, is the global list, so the global doubly linked list of elements in the array, and the black arrows, they show the normal pointers. And the doubly linked list is for the collisions in the hash table. So this is just to show you how this could look like in memory. So with these basics, I will come to the actual vulnerabilities, and the vulnerabilities, I usually call them interruption vulnerabilities, because the whole idea of these kind of vulnerabilities is that I somehow interrupt internals of PHP, like internal functions, and I do something to the variables PHP is currently working on. The problem is that PHP's internal functions are all written as if they are not interruptible. But in reality, they are very well interruptible by a lot of PHP callbacks. And when you have an interruption by a PHP callback, this PHP callback can do all kinds of things like trigger unexpected behavior in the internal function. Sometimes it can cause an information leak, and sometimes it just causes a memory corruption. And actually, no one releases this kind of vulnerabilities except me during the month of PHP bugs. And here are 3 of these bugs that fall into this class of vulnerabilities. And the thing is, these bugs are all not fixed today. Well, actually, one might be fixed, but it's not fixed because they wanted to fix it, but just because they changed the code completely at this point. So it was just fixed by accident. And you will later see why fixing this kind of vulnerabilities is so hard. Like I said, PHP internal functions are very well interruptible, and there are different kinds of interruptions. For example, you have error handlers. When there is an error in the handling of PHP variables, then PHP will internally call the error handler, and a PHP script can register user space error handler. Another thing is, in PHP 5, an object has a toString method, and if an internal function needs a string instead of an object, then it will call this toString function, which of course is an attacker-supplied PHP function, and this could do harm, maybe. You have user space handlers for sessions, streams, and filters in PHP 5, and other types of user space callback that can maybe or maybe not, depending on the internal function, disrupt the function. Yeah, and the easiest way to disrupt the function is to modify this or really destroy the variables the internal function is currently working on. And one feature of PHP that really helps with this, but it's not always required, is the feature called call time passed by reference. This is actually a very interesting feature because it's deprecated since 9 years. Since PHP 4.00, but there's actually no real plan to remove it. The best thing about this feature, there's any directive that says allow call time passed by reference. Most people disable this nowadays, but this doesn't disable the feature, it just disables, or better say, it enables the warning that this feature is deprecated or not. So you just disable or enable the warning, and even if the warning is enabled, you can get around this warning by just don't calling the function directly, but calling the function by call user function. The idea of this feature is actually that the caller of a function can decide that, for example, the third parameter is not passed by value, but passed by reference. So if the internal function doesn't take care of this and modifies a third variable, then this will be reflected in the calling function. You see how you use this in the example, or maybe not because it's too small. You just put an ampersand before the dollar of the variable name, and so it's very easy to use. So how can this actually cause problems? To understand this, we go directly into a PHP function, which is called explode. Explode is used to, explode a string into an array. And here you see, like many PHP functions, the first thing it does, it has a definition of the local variables, then it retrieves the PHP level variables into local variables. Then it tries sometimes to convert these parameters to the parameters it requires, and in the end it performs the action and returns the value. When you look exactly at the conversion and action part, you will see that this it first converts these variables into strings, and later it just uses them and expects this to be string. But the problem is it uses the convert2 macros to convert the variables into strings, and the convert2 macros internally resolve to functions that, when you try to convert an array to a string, then these internal functions will cause a warning or a notice that it tried to convert an array to a string. The same happens for integers. And the same happens for objects. And in PHP 5, you have the exception that when there's a toString method, it will not call the error handler, but it will call the toString method. So actually, this is written as if it's not interruptible, but I just told you it's interruptible. So what is the problem here? The problem is that it later just trusts that it's still a string, the variable string, and it doesn't check it anymore. So what happens? The problem here is when you have a string in memory, you first have the pointer to the actual string, then you have the length of the string, then you have the reference counter, and then you have the type which says it's the string. And now imagine I'm able to somehow convert this variable internally into an array, and just it's in the same place. So now the same memory doesn't see the string anymore. The same memory now points where PHP expects the string pointer. It now points to the hash table. The other thing is, when I do this in-place conversion, it will not touch the other things except the type field. So the red thing, which is the length of the string before, it will not be destroyed. So when PHP accesses this, it actually doesn't access the string value anymore. It accesses the hash table and tries to pull out, in this case, 128 bytes. So this sounds complicated, but actually, when you write an exploit, it's very simple to do. You just set up a user space error handler that uses, in this case, parseString to convert the variable into an array. And the good thing is about parseString, you can also pass some stuff into the array directly. Then you just create a global string variable of the size you want to leak. And then you just call explode with the call user call time passed by reference feature, and pass it the global string. And after that, you just restore the handler on cleanup. And within this error handler, you do nothing else than destroy this. When you do this, the result is that you have a PHP string variable that contains the content of the hash table. And when you look at the content of the hash table, you will see that there's a lot of things in there. You see the hex dump, and actually in the hex dump you see the red values, and the red values are actually ints. And because I know that a fresh table is of the size 8, it has a mask of 7, and so on, because of this, I can exactly determine how big an int is on this system. And because I know what I expect, I can also detect the endiness of the system. The next thing is the green stuff, it's actually a long. So by looking where the long is and how it's aligned and in what order the bytes are, so I can detect the size of a long. And the other thing, the yellow stuff are just pointers into the data segment, and so no, actually there are pointers into the heap. I can see how big pointers are on this system. And additionally, no, not pink. The other color, I just forgot, violet one. It's actually a pointer into the code segment. So you know where in PHP the destructor pointer is in the code segment. So you have a pointer, you have just leaked a pointer into the code segment of PHP. So with all this information, you now can write stable and portable exploits. You can write portable exploits. Because now you know exactly what size the int, the long, and the pointers are, and you know the endiness, and now you can prepare the values in the right size and right direction. So now the exploit function can be used for a similar attack, but we don't convert into an array now, we convert into an int, or into a long in PHP. The thing is, now we just try the same. We do an in-place conversion into an int, and now you see that suddenly the value of the int is used as a string pointer. So in this case, it's just 41, 41, 41, 41, and so PHP tries to create a string from this memory address, like 128 bytes, and returns it to the user. So you actually can leak any place in memory. The only limitation here is that this will not work on Windows Vista 64-bit, because the size of a long and the size of a pointer are different. I will not show how to exploit Windows Vista 64-bit today, but actually by just modification and using the leaks in a better way, you can also exploit this there. But it's a little bit more complicated, and so I will not show this today. The actual exploit is nearly the same like the one I showed before. The only difference is now in the error handler that you don't use parseString, but you use a simple addition of the pointer value that you want to leak. The idea is when you use just the assign add operand, it will reuse the same set well in memory, and so you ensure that you actually use the same memory. It's the same with the parseString function. It's secure that you always have the same piece in memory because it actually uses the same pointer. So it's very stable, this kind of variable switch. So now this was the first exploit. You can use it to leak any kind of memory. And now we go to another interruption exploit that gives you the ability to do memory corruption. We use the uSort function for this. And this looks very complicated, but the only thing you need to see is that there's a parameter retrieval and later on there's the action. And the only thing that's really important there is that we call internally the send-hash-sort function. So we look into the send-hash-sort function. It's again very complicated, but only the thing in the box is important. And the only thing there important is that it will not actually sort the array. It will sort a copy of the pointers to the buckets in the array. So it first creates a copy of all the pointers to the buckets in the array, and then it sorts this list. So the problem here is, well, you also must know that by using uSort, the user can specify a user compare function that is used to compare the elements in what order they should be returned. So it's an interruption for free. So what happens if this interruption does something nasty? Like it just removes an element from the array during the sorting process. So you see our sorting function works on the pointer, on the copies of the pointers, and because the second bucket was removed from the original array, you suddenly sort a bunch of pointers, and one of the pointers is pointing into non-allocated memory. So the other problem is after the sorting is finished, it will reconstruct a PHP array, and in this final PHP array, again, there's a pointer to a memory array that is not allocated anymore. This is for the exploit. So now, how can you use this memory corruption and the information leak to have arbitrary memory access? Right now we have a completely uncontrolled memory corruption, but we want it to be controlled because when we attack the PHP protections, we need arbitrary read and write access to the memory. And we also require the exploit to be very stable. There's no, we don't want any crash at any time. And the idea to how to do this is very simple. We want to replace the bucket we just removed with a fake bucket that points to a fake setwell, to a fake PHP variable, and the fake PHP variable of choice is a string. And this string, we make it as big as possible, which is 2 GB in PHP, and we root it at 0. And so with this string, when we have this string, we can access the first 2 GB of memory just by reading and writing the single characters in the string. And this will look like this. You have somehow, I will show later how, you have somehow reallocated a fake bucket into the bucket that was there before, and this fake bucket just points to the fake string, and the fake string is actually a 2 GB string. Setting this up is very simple. The first thing is you need to set up the fake bucket, and actually you only need to fill in the first 3 elements with well, the index, a 0 because it's a numerical index, so it's not the string length of the key is just 0. And you need a pointer to a setwell. Because you can leak so many things through the information leak exploit, providing this is not very problematic. The other thing is you create another PHP variable where you have the fake setval and the fake setval pointer in there. And you just set up a normal string variable. You know there's a difference between PHP 4 and PHP 5 and PHP before 5.1 and PHP after that. So you actually need 3 different ways to do this, but this is not really a problem. Yeah, and the other thing is because both are within normal PHP strings, you can later just modify these structures. So if you need access to other kinds of memory, not to the first 2 gigabytes, you just change the setval in memory by just changing the string. So, but how do you get this into the same place? This is actually very simple in PHP, because PHP, I already told you, it has some kind of memory manager. And this memory manager has a caching, and this caching ensures that when you free a block of size 14, for example, and you reallocate a block of size 14, it will exactly take the same position, like the previous block of size 14. The only thing you need to do is you need to first clear the memory cache. And you can do this very simple. You just create a PHP function that creates a bunch of global variables, like all strings from 0 to 200 bytes length. And so you'll just allocate memory, and you need to put it into global variables so that it doesn't get destroyed when the function returns. And you just allocate memory. This is how you clear the memory cache. The next thing is, like you already know, you just remove the element from the array to get this removed pointer. And the next thing is you just create 2 very long global variables. You just take a very long name, because otherwise you will end up in the same memory you just want to get into right now. So you just make it very long so that it will not end up in the same space. Yeah. Well, actually, this is trial and error. I tried it with 2. You can use more fake variables. This is just because in one PHP version they broke something, and so if you just try to do the third line, it will crash sometimes in some older version. Yeah, so you just try to create some variables so that the internal function will not reuse the same pointers. And after that, you just create a string that is exactly the size of the bucket that you want to overwrite. You created this on the slide before, and in this moment, you have a fake bucket in place. And this means by accessing this array afterwards, you can just access any piece of memory in the first 2 gigabytes. This would look like this in PHP. You just create an alias to this array, and then you just read by accessing the index in the string, and you can write by just writing into this index. So arbitrary memory read and write. Everything within PHP, everything completely stable. So of course, if you now try to access memory that is not paged, you will end up with a segmentation fault or a bus error. But if you do this in the right way, then you can do whatever you want. So the next thing is, how can we use this to attack internal PHP protections? When you look into PHP, there's one very interesting target, which is called the executor globals. And the executor globals is very interesting because they are, for example, a list of functions, and I told you we want to reactivate functions, so a list of functions is very good. And there's also a list of ini entries. These are the settings that we want to modify, so this is also good. And we have a jump buff. We will not use it later, but actually in older glibc versions you can just modify it to have arbitrary code execution. The problem with this is that the position of this structure is completely unknown to you, and the structure completely changes in nearly every PHP version. So the first problem is, how do you find the structure? In the beginning I tried a lot of things like, the problem is, depending if you have thread-safe PHP or not, it's either in the BSX segment or it's allocated on the heap for every thread. So where to start to search in memory and how to detect an average ever-changing structure. So I tried a lot of things like analyzing the code segment, searching for pointers to this. I wrote a PHP x86 emulator in PHP to get to this. Later, I realized that this is stupid because it can't work, because the pointers, when you have thread-safe PHP, the pointers are stored in the TLS segment, and you can't access FS through this leak. So you would need to know where it's paged in the other memory. And so this all didn't work. And of course, it's completely complicated and it's not portable. And I was thinking how to do this. And after like 3 or 4 weeks, I felt so dumb because it's very easy. There's a very easy way to get to the structure. And this is, I already told you we can leak everything, especially everything that's in arrays. And in the beginning of the executor globals, there are the fields uninitialized setwell. And these fields are used by PHP whenever you access a variable that is not filled, that is empty, that was not defined before. So if you access an undefined variable, actually PHP will use the pointer in there and put it into your array. And because you can leak everything in the array, you can leak the pointer and you can know where in memory your executor globals are. Very simple, but it took me 3 or 4 weeks to find this out. So the next problem is how can we find the actual entries we are interested in these executor globals. I already told you the structure is completely different in every PHP version, but the good thing is the actual elements we are interested in, they are always surrounded by the same elements in all the PHP versions. For example, you have the function table is always at the same offset from, well, depending on the alignment and the size of integers and so on, but it's always at the same position away from the error reporting setting. So what we can do is we know the start of the executor globals and we just change the error reporting value and then we search until we find this change value. And then we found the error reporting in the structure and we know the offset from there to the function table, and so we found the function table. We can do a similar exploit, a similar algorithm for the actually ini directives, because right in front of the ini directives there's a field called lambda count, and lambda count is increased every time you use create function in PHP. So we just create a function, we just look in the memory, create a function, and look again at the same place, and if it changed, then we assume it's the lambda count. We can do this several times to be sure, but yeah. Then we found lambda count, and the field after that is the ini directives. So now we know exactly where the hash table of the function and the hash table of the ini directives. We can read and write hash tables very good, because we can leak everything. The memory, that is, we have the pointers and we can just leak them. So the next thing is, what can we do to disable PHP protections? First, we can just fix the ini entries in memory. And by fixing, I mean any entries are internally in this structure. And this structure, it actually not really changed through the PHP versions. It sometimes changed in the end, but we don't care, because we are only interested in the second element, the red one. Because this element is actually a flag that tells PHP if user code, if HTTPS, or if the web server configuration can change this setting. And we just go through the hash table and go through all the values, and in every structure we just set this to, PHP code can change this flag. And after that, we can just use the ini set function to disable safe mode. We just say ini set safe mode off, false. We can disable open baster by just setting it to an empty string. And we can re-enable the DL function by just setting enable DL to true. So we have disabled nearly all PHP internal protections with just this little trick. Well, actually with PHP 5.3, open baster removing is a little bit more complicated because it changed the the handler for the ini entry to some internal function, but you can just take another entry that accepts a string and just take the handler argument from there and overwrite it in the open base diff structure, and then you can just change it like before. What you actually cannot do here is you cannot reactivate disabled functions. The problem is, like I told before, is that PHP completely removes these functions from the function table. So there's no way that you just change the flag to reactivate them. So what we need to do is to find the original function definition in memory and just copy the pointers from there into the function hash table. So when you look here, this is you see again there's a very simple structure for PHP 4 and a very complicated structure for PHP 5. Both never changed. Well, actually in PHP 5.2 the structure got added an element that makes all this stuff a little bit easier because it contains now a pointer to the extension, the PHP module. This wasn't there before, and I will not go into this because it would make everything too easy. So now the problem is, how do we find these original function definitions? Yeah, well, the first thing is you can do a symbol table lookup, but this is not portable. You can use the module pointer, like I said before, and just go through, then you have a 2-pointer dereference, then you are at the right place. But the other thing is you just go through all the functions that are in the standard extension, for example, and you just take the arcinfo pointers from there. And maybe you take the lowest arcinfo pointer, and this is your base address. And from there, you just scan forward in memory and try to just detect the original function table definition. This detection is very simple because you have an arcinfo pointer, you have the handler pointer, and you have the name pointer, and you just compare it. If it's the same thing you search, and if you found this, then you have found an entry into the function table. You just go backward until you find a 0, and then you have found the start. And yeah, so you found the original definition, and then you can go through both tables and just compare if they contain the same pointers, and if the internal PHP functions don't contain the same pointers, you just copy the pointers back over there, and when you have gone through both lists, then you have reactivated the PHP functions. Actually, this relies on the fact that the compilers always order the structure in this way. It's not guaranteed by the C standard, but like I said before, this is just a fallback for old PHP versions. If you want to attack new PHP versions like 5.2 and above, you just do the 2-pointer dereference, and then you are at the right table anyway. If you want to load dynamic libraries, it's also very simple. You just can use the DL function now, but the problem here is, of course, you need a platform-dependent shared library, so it's not portable anymore. All the stuff I showed before is completely portable. You can just implement it completely portable. It's just one exploit that works on all PHP installations. The other thing is, of course, when you want to load the dynamic library, you need a writable place on the hard disk that is also executable. Otherwise, you can't drop the library there. You also need to activate the enable DL flag. Yeah, you need to restore the function when it was in the disable function list, and you need to adjust the extension dir setting because you can only include extensions from this directory. The last part, I will go through this very fast, is how you can attack x86 Linux systems. The idea is, the first thing is, you can do symbol table like lookups. The first thing you want to do is to find the ELF header of PHP. I already told you you can leak the destructor pointer, which is a pointer directly into PHP code segment. And from there, you can just go back page by page in memory and detect the ELF header or the PE header. And from there, of course, you can go through all the internal tables and look up any function you want. How to do this is out of scope. You can look this up in the specification of the ELF file. Once you found the ELF header of PHP, the next thing you want to do is to find the libc. To do this is very simple. You just go to the imported function list, you just look up memcopy, and from there, from this address, you go again backward until you find the ELF header again, and then you have found the start of the libc. Yeah, so it's no problem to find exactly where in the memory PHP is or wherever the libc is. And after that, of course, you can look up any function in libc. So now what are the protections at kernel level? The first thing is you have the address space layout randomization, and the thing is when you have no NX or mprotect hardening on the server, then the simple address space layout randomization is no protection here at all. Because due to the information leaks, we know all the exact addresses we want to know. Like I just told you, you even know the addresses of libc functions, so it's no protection at all. And actually calling your code from within PHP is very simple. You can just override the handlers of functions, you can override the handlers of any entries, and then just call the function in PHP space, and the code is executed. The moment you have NX or mprotect hardening, this stuff gets a little bit trickier. Of course, you can always do these things like return-oriented programming, or read to libc, or read to mprotect, and read to code. Like I told you before, you can look up all the addresses for free from PHP. And yeah, the only problem is here maybe mprotect. But the thing is, on Fedora 10, I didn't try it on Fedora 11, but on Fedora 10, SE Linux is very broken. And the problem there is, it disallows setting the executable flag for program stack, for heap memory, and for program data segment. But it allows you to change the text segment of the binary back to writable. The actually really funny thing about this is not that this is possible. The funny thing about this is then when you try to setting this page to read and write, then this will just log something like it tried to stop an executable that needed relocation, but actually it didn't stop anything. It just logs this, and the execution works anyway. And if you do the real deal and just set all the flags, read, write, and executable at once, it doesn't even log. I don't know why. Yeah, and so what you do is just copy stuff into the text segment after you set it to read, write, execute, and then you just jump in there. You can do this in a very simple way. Well, it's actually complicated, but like I said before, there are these jump buffs in PHP, but we don't touch them. The pointers are encoded on new glibc versions. Actually, it's no problem here because we could decode the pointers because we all have the correct information, and so we could re-encode the addresses we want, but we don't do this here. Yeah, and when you do this, the other thing is because you know exactly where libc is and PHP, you can search for these kind of statements, and then you build up the stack layout, and yeah, it's not really, it's the normal read to libc. You can look this up because I'm running out of time. The last thing I want to talk about is there's this thing called AppAimer, which works on kernel level, and it allows you to limit the files and well, all these things a process can access, and if it can read, write, executable access. And there's another thing which is an Apache module called mod AppAimer, and this module allows you to well, to change the profile that is used depending on the PHP script that is executed. And internally, this is used by the change head library, and this change head library just stores the current head in this, inside the proc file system, and you can change it there. But to change it, you need to know a random 32-bit token that is used, that is initialized at the beginning of mod app aimer. And you can break out of the current subprofile by just knowing this cookie. And because we can leak any kind of memory, we can do a very simple thing. The first thing is we know where PHP is in memory, so we look up the PHP 5 module pointer, and then we just walk the chain of Apache modules back to the beginning. Then we can just scan for the beginning of Apache in memory. We look up the app top module pointer, and then we again end up in the module chain, and then we scan again. And we do this because sometimes the app ammo module is after the PHP module, and so you don't get there. And when you got this, you just go like 74 bytes after this, the structure in memory or something like this, then there's a 32-bit token. And once you know the token, you can just open proc self attribute current and just send this kind of comments, and you can just break out of your current subprofile and change into any other subprofile if you want. So this is just to show you in-process protection doesn't work the moment you have the possibility to execute PHP code. Of course, when you have mod SSL, you can also use the information leak exploits to steal the private SSL key. You just need to find it in memory. But again, you can just walk through Apache, enumerate all the pools Apache knows, and then you search everyone for the signature of a private key, and then you can steal the SSL private key. So the next thing is the demo. I have to do this very fast. I prepared 2 VMwares for this. Actually, it's both time standard installation of Fedora 11, one time on x86 and one time on x86 64-bit. And this is just a standard installation with a little bit hardening. It has, you can see this. It has a lot of disabled functions. It has an open base dir set. I can't see this. Here's the open base dir and some other things. The safe mode is activated and DL is disabled. So what I wanted to show is I have the same information with the secinfo.php, and I can't read this. I just made a typo, I guess. No, actually, it should be. Well, I don't know why it doesn't work right now, but I just changed to the other server, to the 64-bit version, and now you see you have, it tells you the security settings, the list of disabled function, and it tells you that it tried to execute user bin ID through shell exec, system and exec, and every time it got an error, and it also tried to open etc password D, and again it got open base dir errors that it can't access these files. And now I added a little, well actually if you have questions you can already ask them. The thing is I put a little vulnerability in there. There's a simple include vulnerability in there. And I have a script on the same server that it's called magic.php, and this contains the exploit. And when I call the same with magic.php, it starts with giving out the system information. It tells you that it reactivated the functions, fixed up the init entries, disabled the security features, and then it executed user bin ID. And then you see it actually really disabled it and re-enabled DL. The disabled function list is empty. You see again it was able to execute this stuff. And in the end, it's able to access etc password D. Yeah. So, yeah, question?
So you do this with like either a file format or
Well, you can use any kind of code execution vulnerability. Yeah, in this case, I used an include vulnerability, but if you have an eval injection, you just put the code in in a different way in there. Just using an include was just the easiest thing for demonstration. And the good thing is, of course, well, except on very, very old PHP versions like 4.2, it's always the same exploit. There's just a little bit difference. Like usually you only have to make the distinguish between PHP 4 and PHP 5, but it's once you have written this exploit, it works everywhere. More questions?
Hello? Okay. So, like I believe in PHP 5 or something like in the INI file, remote file includes are disabled, is that correct? And global variables or...
Well, originally in 5.2 there was a feature added. It didn't work completely, so in 5.2.1 you have remote file include disabled. Yeah, but like there are so many other injection vulnerabilities, or like I said, file upload vulnerabilities where you can execute PHP code, so there's always a way.
Anyone else?
And of course, this include vulnerabilities. You only stop the remote ones, but you can still inject something into a log file and just include the log file which is on the server.
I have a question. How has Germany's restriction on exploit code affected your research?
Well, actually, it didn't affect me at all.
So you're breaking the law?
No. The thing is, we had in the last months, we had several decisions where people just accused themselves, and all this stuff ended in nowhere because the court always said there was no malicious intent in doing this. And so if the court doesn't believe I did this to own a lot of servers, then I will have no problem. The problem with the law is that it's actually the interpretation of the judge, but now the highest judges have said it's okay, and so most probably nothing will happen.
Anybody else? Okay.